Welcome to AP Physics. Today we're pondering Kirchhoff's rules. Leading into it, we have a circuit here. It's a regular loop, but we've got batteries in different places. So let's ponder how to deal with those two different batteries. If we think about the batteries, high potential side, the long bar, short bar, low potential side. So the 30-volt battery is trying to drive current to the right, or what would be in the clockwise direction in the loop. The 10-volt battery, high potential side, low potential side, is trying to also drive current to the right, or in a counterclockwise direction. So they're going to basically fight against each other. In this case, the bigger battery wins. So your total voltage delivered to the circuit is going to be your 30 volts minus your 10 volts. Your total voltage delivered to the circuit is going to be 20 volts. In the end, we're working towards finding the voltage between points A and B. But to be able to do that, we're going to need to find the current in the loop. Now that we've got the total voltage, let's consider the equivalent resistance. There are no separate branches. There's only one path. Even though your resistors are separated by batteries, they're still all on one path, so that would be a series. So even being separated, we can still combine them in series. The 8 ohm, the 5 ohm, the 27 ohm, and the 12 ohm. And that's going to give us an equivalent resistance of 52 ohms. Now, if we want to find the current by Ohm's law, I is going to be V total over our equivalent. So that's going to be 20 volts divided by 52 ohms, and that's going to give us a total current of 0.38 amps. Now, if we want to go between A and B, it doesn't matter if we go along this route or if we go along this route. Either way is going to get us from A to B. Looking at what's in the way there, it's going to be shorter if I follow the yellow route. So then V from A to B. First thing we run into when we leave A is a 30-volt battery. We're going from the negative terminal to the positive terminal, or the low potential side to the high potential side, which is going to be positive 30 volts. So the chemicals in the battery are doing work on charges in that direction. Now, when we go through the 27 ohm resistor, we are moving in the direction that the current is flowing. So then that voltage across your 27 ohm resistor is going to be an I times an R. So that's going to be 0.38 amps multiplied by 27 ohms. And that's going to give us a number, 0.38 times 27. It's going to give us 10.26 volts. Now, because we're moving in the direction of the current, that's going to be a decrease. So then I'm going to put that along with my 30 up top minus 10.26 volts. So working from A to B, we have an increase due to the battery. We have a decrease due to the 27 ohm resistor. So then our voltage between A and B will give us about 19.74 volts. Had we gone the other way and gone counterclockwise through the green path, we would have gotten the same value plus or minus some rounding. So when you're moving between one point and another in a circuit, you can follow any path, So you're kind of applying Ohm's law and combining the voltages. Now, what we want to do is push this to a higher level, which is going to be Kirchhoff's rules. Our end goal is to be able to deal with more complex circuits, such as this one. In this circuit, you've got 3 different batteries in different places. You've got different resistors on the different branches. You can look at it, you can try to break it down to a series circuit or a parallel circuit or a combination, but because your batteries are in 3 different places, you cannot redraw it any way that's going to show just series, just parallel, or a combination. So then our straight series and straight parallel rules that we've used previously will not work on this circuit. We need other tools, and our other tools are Kirchhoff's rules. So let's come back to this circuit. Okay, Kirchhoff's rules, very logical, and what they allow us to do is to be able to set up a system of equations so we can analyze more complex circuits like the one we just saw. So let's start with our junction rule. Junction rule, thinking in terms of current, if I have 10 electrons flowing into this junction here, okay, then what's coming out the other side? Some's going to go up, we'll call that I2. Some's going to go down, we'll call that I3. And our original current we'll call I1. Well, junction rule, basically logical, whatever goes into the junction has to come out the other side. So then I1 is equal to I2 plus I3. So they may or may not split up equally, depending on the resistance in the path. So if we follow the number of my 10 electrons, then maybe 8 electrons go this way. That would mean the other 2 electrons go this way. They will split up. You don't lose any electrons at a junction, just like if you're going down a hallway that splits into a couple of paths. The same number of people that enter that junction in the hallway have to come out the other side. Okay, so the junction rule basically is that the sum of the currents entering a junction equal the sum exiting that junction. Now, loop rule is kind of like the example we just did, okay? But loop rule, instead of applying currents like the junction rule, is dealing with voltages. If we start at any point on the circuit and we go all the way around the circuit, coming back to that point where we started, okay, I should run into voltage increases and decreases, but the total voltage around any closed loop should be 0. If it was not 0, you'd gain a little the first time, then you'd gain a little the second time, then you'd gain a little the third time, and pretty quickly you'd have so much extra energy. Conservation of energy, any gains and any losses will match out. Every bit of voltage or energy per charge supplied by the battery is then dissipated as those charges move around the circuit in that complete loop. In an equation, the voltage of a battery, that's just the EMF. Okay, the voltage across the resistor, that would be Ohm's law. So V, in this case, would be I1R1, and my other resistor over here would be I2R2. Now, this battery, based on the direction that it is facing, negative terminal there, positive terminal here, will be pushing current in that direction shown by the arrow, which would be a clockwise direction. So then moving through resistor 1, the current would be moving that direction. Resistor 2, shown by the blue arrow there, okay, but it's the same current, so we can take that 2 off of there. it is the same current value. So then moving around my circuit from the blue, now red dot clockwise, as I moved across resistor 1, I'm moving from the high potential side by the battery to the low potential side. So that would be a drop. I1, just IR, 1. Okay. And I get to resistor 2, and that would be a drop also. IR2, so that would be a negative. If you are moving in the direction current is flowing, current always flows towards low potential, then those IR terms are going to be negative. If we happen to have been going counterclockwise, then the way we would be going around the circuit would put those as a positive. Okay, and that'll become more apparent in the next example that we do. Now, as we continue to round around past R2, we go across the bottom of the circuit and we get to the battery. We go from the negative terminal to the positive terminal, which would be an increase in voltage of the EMF. And then my total is 0. Total of the losses, total of the gains, as long as I go all the way around, so no matter where I start, I have to go all the way around a loop back to the starting point and account for every voltage change. Okay, now let's go back to the original example we had just previewed a minute ago. We want to find the current in each branch. There are 3 different branches. One branch is up here. One branch is across here. And one branch is down here. So we want to find the currents in each of those branches. So the first thing I need to do, okay, is specify them. We're going to call them an I1, an I2, and an I3, but we have to draw them in some directions, okay? So I'm going to call I1 the current in the top branch, and just looking at the batteries real quick in terms of which direction they will drive a current. Positive terminal there, negative here. So that top battery is trying to drive a current to the left. Okay, the battery on the middle branch, negative terminal, positive terminal, it is trying to push a current to the right. And the bottom battery, negative terminal, positive terminal, it is trying to push current to the right. I'm going to use that kind of as a guide for what direction I put the currents. In the end, if you choose a different direction to draw a current than somebody else, you'll still get the same values as long as you do the math right. You just have to have the signs correct. Okay, so now based on that, the 12-volt batteries are going to dominate the 6-volt battery. So I'm going to start with I1, starting at the junction on the left, and I'm going to have that current going around in that counterclockwise direction for all of the yellow. I'm going to call I2 along the center branch, and I'm going to have that going horizontally to the right, and I'm going to have I3 on the bottom, the blue branch, and I'm going to have that going around here. Now, we have 3 unknowns, I1, I2, and I3. So that means we're going to need a system of equations. And in that system of equations, we need 3 equations. One of those equations is going to come from the junction rule, and 2 of them are going to come from the loop rule. So for the junction rule, if we look at the junctions, I1 goes around the top, and at the junction over here on the side, right there where I put the blue dot, I1 goes into that junction, and I2 and I3 come out of the junction. So then I1 is equal to the sum of I2 plus I3. Now, the loop rule, you actually have 3 loops in the circuit. The top loop, the bottom loop, and then the entire outer loop, which would be the green, or not the green, but the yellow and the blue. You cannot get your system of equations just by using 3 applications of the loop rule, because top loop plus bottom loop equals outer loop. Okay, so I'm going to do a loop rule for the top loop and a loop rule for the bottom loop. So on my top loop, I can start at any location I want. So if we start, I'll go right up there in the top left corner. I'm going to start there, and I'm going to go around in a counterclockwise direction, and I'm going to spell out each different voltage loss or gain, okay, as I go around that top loop until I get back to that pink spot. So on my top loop, the first thing I run into is the 8 ohm resistor. So then the voltage would be I times R, which would be I1 times 8 ohms. Looking in the direction that we're going around the loop, we are in the direction of I1. Current flows from high to low, so this would be a negative. When I get down to the blue dot, then I take a right, and I go through the 12-volt battery from negative terminal to positive terminal, so that's an increase of 12 volts. I continue on across, and I run into the 10 ohm resistor, and I'm moving in the direction of I2, so that's going to be a drop. That would be I times R, I2 times 10 ohms. I get over to the junction on the right side, and then I go up to the yellow part again, and I run into the 12-volt battery, negative terminal to positive terminal, so that's an increase of 12 volts, and my total is going to be equal to 0. Okay, doing a little math on this and simplifying a little bit, this is going to be a negative 8 I1 minus 10 I2 plus 24 is equal to 0. Now if I go down to the bottom loop, again, it doesn't matter where I start because I already have the blue dot. I'm just going to start there at the blue dot, and I'm going to go around also counterclockwise. So as I head down the left side and then across the bottom line, I run into the 6-volt battery first of all. Well, that's going to be from negative terminal to positive terminal, so that's going to be a positive 6 volts. And then I run into the 18 ohm resistor in the direction that I3 is moving. So then I'm going to have a negative I3 times 18 ohms. Then I get to the junction on the right side, and I have to move across the green. When I move across the green, I'm moving the opposite direction of I2. And so then I'm going to have moving from the low side of the 10 ohm to the high side of the 10 ohm. That's going to be a positive I2 times 10 ohms. And then I run into the 12-volt battery, moving from the positive terminal to the negative terminal. So that's going to be a negative 12 volts. And my total is going to be 0. Doing a little bit of algebra on this, this is going to be 10 I2 minus 18 I3 minus 6 is equal to 0. So now we've got 3 equations right there, and right there. 3 equations, 3 variables. We can solve this down. The easiest way to solve down this system of equation is to put it in your calculator. And on the AP exam, you're allowed to put it in your calculator and solve it down. So if you know how to put that in your calculator and solve it, do that. If you don't know, I would recommend learning. I've linked on the Week at a Glance for today a short video that talks you through how to input a system of equations into the calculator and to be able to solve those down. Okay, so based on that, I'm going to go ... And when we do the algebra to be able to solve these down, we get an I1 value of 1.51 amps, an I2 value of 1.19 amps, and an I3 value of 0.33 amps. Had we drawn one of our arrows for I1, I2, or I3 in the opposite direction that we showed them, then we would have gotten a negative number for one of these. We did not, so all of the currents are flowing in the directions that we specified on the diagram. It's really important that you mark up your diagram when you're solving these problems down, and also that you are very careful keeping track of the 1s and 2s and 3s on your different current values. Let's consider one more example. I would encourage you to pause the video here for a second, specify your currents, and set up the different equations, and then double check with the video. So, you should have set up the equations by now. So if I was going to analyze this circuit and set up my 3 equations, I would first of all have to decide what direction I'm going to draw the currents. So on my batteries, my 45 volt battery, negative terminal, positive terminal, it's trying to drive a current to the right. My 80 volt battery, negative terminal, positive terminal, it is also trying to drive the current to the right. 80 volts is going to win out over 45 volts. So then I'm going to specify in my bottom branch here, I1 around in that direction. I'm going to have it force the current across the middle branch. I2, just looking for somewhere to draw it. We'll just draw it up there. There's I2. And then I3 around the top branch. Okay, if you specified your current numbers differently in the different branches or in different directions, you can still translate the equations that we'll come up with here, and you should still get the same current values, okay, even if you specified different numbers on different branches or different directions. So then to solve this system down, we need 3 equations. One will come from our loop rule, as before. 2 will come from the junction rule. So on our loop rule, into the junction on the right side there where I just put the blue dot, I1 goes in, I2 and I3 come out. So then I1 is equal to I2 plus I3 by the, hold on one second, I'm going to move loop and junction around. That's a little bit better. So 1 by the junction rule, 2 by the loop rule. Now, by the loop rule, I'm going to do the top loop and the bottom loop. So my top loop, I'm going to highlight just so I can reference more easily. My top loop is going to be around there in yellow, and my bottom loop is going to be around here in green. So on the top loop, arbitrarily starting anywhere you want, okay, I generally will pick that upper right hand corner, okay, and the current's flowing counterclockwise there, so I'll just go with the counterclockwise direction. So in that top loop, I go down the left side, following the yellow across the middle branch. I run into the 40 ohm resistor. I2 is going to the left, but I'm moving around the circle to the right, so I'm going against the current flow. So then that would be from low to high, so this would be a positive IR. So that would be I2 times 40 ohms. Now we continue to move across and we run into the 45 volt battery. we move across to the right. So that's from the low terminal to the high terminal. So that's going to be a positive 45 volts. And then we get to the right junction and we go up the yellow up to the top branch and we run into the 30 ohm resistor. Now I3 is moving left in that top branch. We're rotating around left, so we're in the direction of current, and current flows to the low potential side. So then negative I3 times 30 ohms, and that's equal to 0. So cleaning up our equation a little bit, this would be 40 I2 minus 30 I3 plus 45 is equal to 0. On the bottom loop, let's see, we'll go put a dot right there, and I'll go counterclockwise again across the green. So then if we're doing that, I go down the left side, run into nothing. First thing I run into is that 80 volt battery, negative terminal to positive terminal, so that would be an increase of 80 volts. And then we continue to the right and up the right side through the 20 ohm resistor. We're in the direction of I1. Current flows from high to low potential, so that would be a decrease of I1 times 20 ohms. We get to the blue dot junction on the right side, and then we go left to the 45 volt battery, high potential to low potential, so that's going to be a drop of 45 volts. And then we get to the 40 ohm resistor. We're moving in the direction of I2, so that will be a negative I2 times 40 ohms is equal to 0. Sorry, I kind of crunched it in there. Cleaning up the equation a little bit, let's see, I'm going to have 20 I1, that's a negative, minus 40 I2. Clean that up a little bit. And then an 80 volts minus 45 volts, that's going to be negative 35 volts is equal to 0. And let's take that back. How about a positive volts? And I was pausing you to look at it because all the terms were negative and that didn't look right, okay, because you have to have gains and losses. So then there's that one positive in there that compensates. So now we've got three equations. Right here, right there, and right here. So again, to be able to solve this down, we would plug this into the calculator. You can also solve it down doing graphing, substitution, something like that. Those methods are going to take you longer. Plug it into your calculator and solve down. I'm going to go dot, dot, dot. So then when we solve this down, I1 is equal to 1.63 amps. I2, 0.058 amps. And I3, 1.58 amps. These problems take practice. Your key is be very organized, okay? Make sure you keep track of which current is in which branch. Again, what direction you draw the arrows doesn't matter, but make sure you keep track of which is I1 and which is I2 and which is I3. And then the signs on each of the terms. If you're going from negative terminal to positive terminal on a battery, that's an increase, so it's positive. On the resistors, if you're going in the direction the current is flowing, it always flows to low potential, so that would be a negative term. If you are going around the circuit against the direction the current flows, then it would be from low to high, so that would be a positive or an increase. Ponder Kirchhoff's rules.